Hello all. This is the 16.1 video. Let's see, okay, as I was saying, this is the 16.1 video. I need to share my screen. Okay, going to iPad now. Let's see, oh, we got a bunch of work from earlier today. 16.1. Okay. Vector fields. Okay, so we're starting chapter 16. This chapter kind of titled Vector Calculus. Not too much different. I mean, I think it's a natural progression from our previous material. So 16.1 it should be a pretty short section and nothing too difficult here. Okay. So what have we seen so far in this course? And really, not just in this course, we could add another layer to this. Let's consider our Calc 1 and 2 courses as well. Okay, how about, let's see, let's call it H, I suppose. So maybe in Calc 1, we started with functions of a single variable, right? The stuff we're most used to, f of x equals y. Okay, and then in this course, we started seeing other forms of these functions. We saw the vector valued functions, where we took a function of a single variable t, and the function gave us a vector output. Okay, we could do examples for each of these. So let's see. For the single variable functions, we have something like that. All right. Then we had our vector valued functions, so that could be something like what? Maybe we would write it like this. So maybe we would have like a function like this. We're talking about our variables t, so maybe we have an independent variable t, and then it gives us a vector, right? All right. So we saw single variable functions, we saw vector valued functions, and then most recently in chapters, did we start multivariable functions? Was it chapter 14? That sounds right. We saw the multivariable functions, which took a vector input and gave us a single number output. So something like f of x, y, z, right? Or, let's see, we could do f of x, y equals z. So for example, z equals x squared plus y cubed ln of x, something like that. This is the stuff we've been dealing with most recently. So we have these types of functions, and maybe you can kind of guess what the next one would be. Okay, we have functions from R1, R to R, which we can think of as R1 to R1. Okay, then we have functions from R to Rn, Rn to R. The next natural step is to consider functions from Rn to Rn. Okay, so let's consider functions of this form. That's what we're going to start looking at in this section. Now, don't worry about, we're not going to really develop a whole new theory of integration and differentiation for this stuff. It's all based on the previous material, and really we're gonna do some different things with functions of this type. Okay. So in particular, as usual, we're going to be considering mostly the cases R2 to R2 and R3 to R3. Like we're thinking about these spaces we can visualize easily. Okay, but once again, these concepts kind of scale up to higher dimensions, but in almost all our practical applications for this stuff, we're going to be considering R2 to R2, R3 to R3, and that's mostly what the book presents. In fact, for this section, the book is mostly concerned with R2 to R2 because it's easier to draw, I suppose. Okay, so what does a function like that look like? Okay, and we're going to talk about what to call this type of function in a moment, but just think about what this type of function would look like. So for example, let's consider the case for R3 to R3. Okay, let's see. So what does a function like this look like? Its input is got three-dimensional input, right? So our input would be x, y, z, for instance, and then its output is three-dimensional, right? So it's our output is a vector. And don't worry about what's in the vector for a minute. Just for now, just note that okay, its output is a three-dimensional vector. Okay. Now, similar to let's call this J. Similar to our vector valued functions, right, which we talked about up here. Where? Here. Okay. So similar to our vector valued functions, when I have a vector valued function, think back to your chapter 13, I believe. When I have this vector valued function J from R to R3, I could kind of think of like my output is going to be a vector, and then I could think of each of my components of my vector as being a function, right? So when I had this vector valued function J, I thought of it like this, where I have this three-dimensional vector, and then the first component is f of t, second component is g of t, third component is h of t. Okay, and then we have a similar thing for these for this case, R3 to R3, right? Our input, the only difference is our input is three-dimensional, not one-dimensional. So we have this x, y, and z, and it's giving us this vector, this three-dimensional vector. And I can think of the first component as a function f1 of x, y, z, and then I could think of the second component as maybe a different function, f2 of x, y, z, and then the third component is f3 of x, y, z. So for example, an example of this would be, let's say I have the function of x, y, z. Okay, let's talk about a specific function. Maybe my specific function is like x squared y plus z. And then my second component would be 3z minus ln of x, y. And then maybe my third component is just, 1 minus x squared z, y. Okay. So this would be an example of what we mean, right? We have three-dimensional input, and then each of these, we have a three-dimensional output, and then each of these components is maybe a different function of our inputs. Okay. So here's another example. Let's say I have this function, capital F of x, y, and so that's a two-dimensional input. It's giving me a two-dimensional output. So this is, again, the form R2 to R2. Okay, what does the function look like? First component is x plus y. Second component is x times y. So for example, what would f0 of 0, 0 be? Well, that would be, I plug 0 in for x, 0 in for y, 0 plus 0 is 0, 0 times 0 is 0. Okay. What about f of 1, 2? Well, that would be 1 plus 2, which is 3, and then 1 times 2, which is 2. And what about, let's do one more. How about f of -3, 1? Okay, what would this be? -3 plus 1, -2, and then -3 times 1, -3. Now, unlike our previous types of functions, this is going to be a little hard to graph, and there's not really a great way to graph it. So let's kind of talk about the progression of our graphs for these different types of functions. Just real quick. So really easy, and maybe it wasn't easy at the time, but in retrospect, maybe it seems much easier now. Functions of a single variable, right? Those were easy to graph. I have my input x, I have my output y, and I basically take these x values, plug them in to my function to get y values, f of x's, right? And then all those, I plot the point x, f of x, right? And I plot all my x and y, I plot all my x and y values, and that gives me a nice curve, right? And this is, we call this the graph of our function, right? That's the idea of what's going on with the graph. And then for multivariable functions, okay, if this is low enough dimension, right? If this is like dimension 2, and then we graph, or then our out, it's R2 to R, we could graph this in the 3-dimensional space, right? We consider this horizontal plane our input xy, and then this vertical line is our output. So for example, I have maybe this input on the xy plane, and I plug it into my function, and it gives me this value up here. Okay, so this will be the point x, what? It'd be the point x, y, f of xy. Okay, right? And then I plot all my points, and it gives me a surface, right? Okay, maybe that's the surface for, this domain. Okay. All right. And even my vector valued functions, we saw a way to deal with that, but these functions R2 to R2, we can't graph them in this way, definitely, because there's too many dimensions, right? So if I tried to graph them in the way I've graphed my single variable functions and my multivariable functions, I don't really have enough dimensions. Like I would need what would I need? I would need to graph R2 to R2. I would need 2-dimensional input, 2-dimensional output. And then if I was trying to get a graph, if I was trying to graph that, I would need to be able to draw R4. And again, I can't draw a 4-dimensional space. Okay. And you can't either. There's no good way to graph it. Okay. There are ways around this. One way is one way to think about it is like to draw your, and not to kind of try and put your graph together, have it kind of in pieces. So maybe this is my input R2, and maybe this is my output R, which is also R2. So maybe I kind of visualize it like this, like here's my input, X1, Y1. And then I plug it into my function, and it spits out a point, X2, Y2. And so I could think of it at least as kind of my function is the arrow that takes, this input to this output. All right, that's one way to visualize it. It's kind of a cumbersome way to graph things, right? And it wouldn't have much practical value. A better way to visualize it, and this is not, it's still kind of wanting. It's not a perfect way to graph these things. Another way to visualize it is kind of on top of each other for R2. Okay. So let's say this is my 2-dimensional space R2, right? And I take this point AB, and I plug it into my function f. And let's use specific numbers. Let's say I take this point, this would be like what, 1, 1, roughly. So let's say I plug 1, 1 into my function, and I get the point, or I think of it as a vector instead. Maybe it spits out the vector 0, 4. Okay. So one way to graph this is to draw this output as a vector starting at this point here. So I plug in 1, 1 to my function, and I get the point 0, 4 out, which would be roughly this vector, right? Okay, and that would take me up to what? We're not going to worry about specific numbers. We're usually just going to be looking at the vectors, but in this case, it would take us up to the point what, 1, 5. Okay. So that's one way to do it. And then it's obviously not even possible to do these arrows for every point, right? I couldn't draw an arrow for every single point. So one way we get around this is to draw just, a selection of these arrows. Let me take a pause here for a moment. Apologies. Let's continue. Where were we? Connect my iPad again. There we are. Okay, so I believe we were discussing a way to not graph in the sense we're used to, but somehow present information on these functions. And we haven't given a name to that, but I'm going to name this type of function in just a moment. Okay. Okay, so one way to at least graphically show what's going on with these functions is to draw the input space. Okay, so our inputs are coming from R2, as we said, and then we're going to take a point, plug it into our function, and get an output, and then we're going to graph that the vector output with our starting point being at our input. Okay. And as I said, it wouldn't be practical to do this for every point, right? So it's not really going to be a graph like we're used to, because normally for a graph, like for a graph of a function of a single variable, I have the smooth curve. And what it is, it's essentially like I've taken every single possible x value and plugged it in and got my y values, and I graph them together. And when I graph that infinite number of inputs and outputs, I get this nice smooth curve. Okay, well, that's not practical here, right? In this case, right? I can't plug in every single one of these points and then draw these vectors that are coming off of them. Okay. All right. What I'm going to do is I'm just going to pick a bunch of points that will give me an idea of what's going on. And they're usually very orderly placed. Maybe maybe there's a very clear pattern to the placement of these points. And I plug all these points into my function and get my outputs. And then I get these, these output vectors. Okay. Okay, and I kind of graph all these points together. Graph all these little vectors together. And I get some kind of display. Okay, and now maybe is a good time to go over the terminology. let's kind of go over the terminology, and then we'll come back up and do this example. Maybe it's clear that maybe you can kind of see why we call this type of function, here, the f from R2 to R2, we call it a vector field. Okay, now that name, maybe it sounds confusing to you. Okay, vector field, what does that, I don't know even, what does that even mean? But it seems to make a lot of sense when I kind of think of the graphs of these types of things. It kind of looks like a field of vectors, right? It's now, you know, in mathematics, field and vector have very specific and specialized meanings, but you know, just kind of intuitively, okay, it kind of makes sense to call this type of function a vector field. Essentially what you're getting out, you're plugging vector in, you're getting vector out, and then when we graph these things, we graph essentially just a space of vectors. Okay, so we call this type of function that we're looking at in this section 16.1 of vector field. And what we've drawn here, now the vector field is the function, okay? So this is the vector field, okay? And then this drawing here that we're making is just kind of a graphical representation of the vector field. So I don't want you to get confused about what's what, okay? So the vector field is the function, and then this drawing that we're making is just kind of a pictorial representation of that function, okay? So let's see a specific example, okay? Here we're just doing kind of, you know, wishy-washy stuff. So let's look at a specific example. Let's look at the vector field given by this function here. Okay, so f is our vector field. In other words, it's a function from R2 to R2. Okay, and it's defined like this. First component is x plus y. Second component is x times y. Okay, so what I'm going to do is to get the graphical representation, and that's usually what we want, and that's mostly what the homework is. We want these graphical representations of this function. I'm just going to graph a bunch of points. Okay, so let's start with 0, 0, and we already found some values earlier in the previous example for this vector field, right? So we saw f of 0, 0. Well, that was equal to the vector 0, 0. Okay, and let's do our vectors in blue. Okay, so at the point 0, I get the 0 vector. Okay, what about at the point 1, 1? Okay, so again, I plug 1, 1 into my vector. Excuse me, I plug 1, 1 into my vector field, my function f. And what is the output of the point 1, 1? That would be the vector 2, 1, right? So at this point 1, 1, okay, my output is 2, 1. So I draw the vector that goes over 2 and up 1, which would be roughly this vector, right? Okay, so at that point I have that vector. All right, now let's plug in, how about we plug in 2, 1? Okay, so let's say this is the point 2, 1 here. I plug that into my function, and what do I get? I get the vector, what, 3, 2. Okay, so that's the vector that goes over 3 and up 2. Okay, so let's say this is 1, 2, 3, 4, 5, 1, 2. Okay, so maybe at that point I have that vector. And then let's see, what if I plugged in the point, how about 3, 1? What if I plugged in this point 3, 1? Well, now my output would be what, 4, 3. So I go over 4 and up 3. Right? Okay. And then I could do this same process for other points. Let's say I was at this point here. What about at the point, this would be the point 0, 1, right? I plug that into my function and I get 1, 1, 0. Okay, so that would give me this vector. What about the point 0, 2? Plug that into my function and I get what? I get 2, 0, which will take me here. Okay. And then at 3, 0, 3, I'd get, this vector and so on. And then let's see, let's do some points on this left side. Okay, how about the point -1, -1? I plug that in, I get -2, 1. So that would give me this vector. And let's see, it looks like I made, now in retrospect, it looks like this vector that we started with should have gone to here. Okay. Okay. And let's try this point. How about -2, -1? Plug that into my function. Okay. And that's going to take me 3 units to the left. And what? 2 units up. Okay. So you see what's happening, I hope. Let's see. How about if I plugged in, I think that's enough. Okay, so these vectors should all be good. And then what if I, let's say just for the sake of argument, I plug in a bunch of other vectors and I get, stuff going like this, etc. Okay, so it kind of gives me a picture of what's going on, and maybe it doesn't seem very orderly. That's because this function is probably not very good. Okay, I made this function up on my own. We're going to see in the text that there's a lot of nice functions that give a lot of nice, kind of orderly looking vector fields. At least, their representations look very nice and orderly. Okay, so what's going on with vector fields? Why do we care about them? Well, there's just a ton of real world examples for vector fields. And that's most of what the section of the textbook gives. It just gives a bunch of examples. It gives specialized uses of these vector fields. So in the textbook, in the section, you'll see a lot of this terminology. Velocity field, force field, electric field, gradient field. Okay, what are all these? Do we have to learn a bunch of, do we have to learn 4 different things? No, these are all just vector fields. Okay, these are all just types of vector fields. So we don't need any new mathematics for these 4 different types of vector fields. Okay, this is just like applications of the vector field. Okay, so what would a velocity field be? A velocity field is this would maybe be the easiest kind of real world example to show. What would a velocity field be? Let's say we have like a map. Okay, let's say we're talking about weather, and in particular wind speed and direction. Okay, and we're talking about a map centered, maybe this is whatever location you want, maybe the center of our area, and then we're talking about the wind speed and direction all around this point. Okay, so maybe the wind, maybe we have, you know, maybe we're predicting the wind or modeling the wind, however you want to say it. But let's say the wind velocity in miles per hour is given by this function here. Okay. Okay, how about no, let's say how about this 2x 2y. Okay. Let's say this function describes the wind. Okay. So what I do is I take a location, a point x, y, I plug it into my function, and that function spits out the wind velocity at that location. Okay, so like the magnitude of this vector, let's call the vector v. The magnitude of v would be what? The actual speed. Okay, and then the vector itself, you know, let's say, okay, this is saying, okay, it's moving 2 miles per hour in the x direction, 2 miles per hour in the y direction. So if I graph that vector, that's kind of giving me wind direction, and then the length of that is giving me the wind speed, right? Okay. So this would be a very common example, and something you see with like hurricanes and things like that. And obviously the wind patterns are very complex, but you know, this is a very simple example. You know, maybe for a hurricane, you'll see these little graphs that show the wind, how the wind is spiraling around, and etc. See graphs like this. Okay, that's a velocity field. Okay, and this is how they're derived. All right, so let's say this is my function for wind speed and direction. My velocity, it's giving me a velocity field. Okay, so let's graph several points again. So let's take the point 1, 1. Well, I plug that into my function. It spits out what? 2, 2, right? So it's a vector that goes over 2 and up 2. Okay, so it'd be this. Okay. What if I plug in -1, -1? Well, that would give me -2, -2, right? What if I plug in 2, 1? Well, that would give me a vector goes over 4, up 2, right? So I give me like this. Same thing here. Okay. Okay, so maybe I get a vector field that looks essentially like this. Okay. And this is, what do these arrows represent? They represent the velocity of our wind, so the speed and direction of our wind. Okay. Now, these arrows are getting kind of big, and the larger magnitude we have, the bigger these arrows would get, right? And maybe it's not really practical to draw these huge arrows. So sometimes, not always, but sometimes these arrows will be scaled down so they're all kind of manageable size. So if all we care about is direction, for instance, the direction of our wind, maybe I plug in my points and then I just draw all of my arrows with the same length. Okay, you'll see that a lot. Okay, so maybe they all have like little 1/2 unit length or something. The other examples, we use these vector fields when describing these other examples, like force at a point or electric charge at a point, etc. And these are interesting examples from physics. And if you are partial to physics, I would check out these examples on the book. There's nothing, as I said, there's nothing new mathematically here. Maybe they give some formulas for physical laws, things like that, but there's no new techniques here. It's just specific examples. The one thing I think that stands out that we should talk about, the one type of vector field that maybe is not just well, that's going to be important from a mathematical standpoint, is called the gradient field. Okay, so what is the gradient field? A gradient field is a way to start with a multivariable function like little f from R2 to R, and then get a vector field, that function R2 to R2. Okay. Okay, so let's say we start with a function f, little f from R2 to R, and let's say it's differentiable. So I can take its gradient, right? That symbol del f. Okay, I take its gradient, which gives me a vector. And what is that vector? Remember, that vector is the partial derivative with respect to x, partial derivative with respect to y. Okay, so I take the gradient, and that gives me a vector. Okay, and really, I can think of this as a vector function, right? Or excuse me, a vector field. I can think of this as a vector field. So for each point, I can plug a x y into this gradient, and it's going to give me different values of this vector, right? Okay. So this gradient gives me a vector field. Okay, and these gradient fields have special properties, and we're going to be interested in them later on. We're going to discuss that a little bit in just a second, but let's play around with gradient fields a little bit. Let's say I'm asked to plot the gradient field for this multivariable function. Okay, so this is my function little f. First thing I need to do is I need to find my gradient. Like this is a function R2 to R, right? I need to find my capital F R2 to R2, which, since we're looking at a gradient field, that capital F is going to be given by the gradient. Okay, so I need to figure out what this function is first. Okay, so what is that gradient function for my little f? Okay, so what I'm asking is, what is the gradient? If this is my multivariable function, then my gradient is going to be what? 2xy and then x squared minus 3y squared, right? Okay, so that's my my gradient. And then what would my plot of my gradient field look like? So now I'm just going to graph this, or I'm going to plot this gradient field. Okay, meaning, again, I'm just taking values of x and y and plugging it into this function here and seeing what I get out. So for instance, if I started at the point 1, 1, let's see, I would get what? 2, negative 2. Okay. Let's draw this a bit smaller. Okay. So if I'm at 1, 1, my vector is 2, negative 2, which would bring me here. If I'm at, how about if I'm at 2, 1? That would put me at 2 times 2 times 1, so 4. 4 minus 3 is 1. Okay. So my output at 2, 1 is the vector 4, 1. So to plot that, I would go over 4 and up 1. And then I could plug in a bunch of other points and maybe see some sort of pattern. You know, I haven't graphed all these points, but let's say it kind of goes like this. Okay. For the sake of argument. Okay. All right. So again, nothing terribly new here, right? It's just finding a gradient, then plotting the vector field from there. Now, gradient field, these gradient vector fields are going to be particularly important. They have nice properties. Okay, when the vector field, let's say my function f, okay, my vector field R2 to R2, let's say it happens to be, let's say this is actually the gradient of a function f of xy. Okay, well, now this gradient field is going to have nice properties that we're going to be able to utilize for applications, and we're going to cover that in a later section. I just wanted to cover some terminology first and a quick little concept. So some vector fields, but not all, are gradient fields. So it's definitely possible to have a vector field f from R2 to R2. It's definitely possible to have a vector field that is not the gradient of any function. Okay. But as I said, if it is the gradient of some function, it's going to have nice properties. So we would like to be able to tell when this is the case. Okay. So, sorry, somebody came in the room. I was distracted. There's some terminology to go along with this type of vector field. So if a vector field is a gradient field, we call the vector field conservative. Okay. And we would call the source, that little f that's giving us our gradient, we would call that the potential function. Okay. So digest this little block of text here. Pause if you need to. And that should be all the material, I believe. We're ending just on some terminology. We're going to see some tests in later sections to determine if, we're going to be given a vector field f, and then we're going to be asked, okay, is this vector field, is it a gradient field for some function little f? Okay. So we're going to be asked this question: is this vector field f, is it the gradient field of some function little f? Okay. If so, we would call this a conservative vector field. Okay. And then we would call this not the gradient, but we would call f the potential function. So just ending on some terminology there. And really, that's all there is to it. It's this section 16.1 is just about really the concept of the vector field and plotting these plots. So not too much there. All right, that's all for this video. Have a good day.